Full text search and fuzzy indexes. All the indexes discussed so far assume that you have exact data and allow you to query for exact values of a key or a range of values of a key with a sort order. So we assume that all index before were in sorted order. What they don't allow you to do is search for similar keys such as misspelled words. So this is actually how the search engine works, kind of how the search engine works. You have a search and you have a document or other multiple forms of data that could match those search words. For example, full-text search engines commonly allow a search for one word to be expanded to include synonyms of the word, to ignore grammatical variation of words. So this is the key, not just the synonym of the words, but also the variants such as one letter or one to two letter plus or minus on the words, and to search for occurrences of words near each other in the same document, and support various other features that depend on linguistic analysis of the text. So it also cover the words in that same document, how often it occur in that same document, and the various features that depend on linguistic analysis. So there's also linguistic analysis that people or language administrator do to analyze their text. So this is it. To cope with typos in documents or queries, Lucene is able to search text for words within a certain edit distance. An edit distance of 1 means that one letter has been added, removed, or replaced. So that's what I mean by plus or minus. So that's how they were able to cope with typos. So this edit distance could be 2, 3, it could be set depending on your setup. As mentioned, in making LSM3 out of SS tables on page 78, Lucene uses a SS table-like structure for its term dictionary. So this search index or search, kind of like a search engine, use a LS table or SS table that is being used by LSM3 for its dictionary. So remember, the dictionary is just a key value pair in Python, kind of like how you would search for a word or a value fast using a key. This structure requires a small in-memory index that tells queries at which offset in the sorted file they need to look for a key. So this is actually how the full text search is fast, is because it's an in-memory keys, kind of like an LSM3, that is indexed to the offset of the actual value in the disk. In level DV, this in-memory index is a sparse collection of some of the keys. But in Lucene, the in-memory index is a finite state automation over the characters in the key, similar to a trie. So remember the trie we discussed that also kind of mimic the search engine or the trinode, the data structure we discussed in data structure and algorithm, which kind of mimic how the AI predict the new text today. This is also how they do this here. So in level DB, this in-memory index is a sparse collection of some of the keys. So the sparse but in Lucene, the in-memory index is a finite state automaton over the characters in the keys. So it's kind of like the first letter of the word that is offsetted, like when you type letter K on the search bar. The value, the offset value, all the offset value that is related to that, kind of like in a try, would pop up as a search in your search engine, like kind of like in Google when you type letter K, all the uh, suggested word to that will be shown, but it's not gonna be the 16, it's the most likely. So they also, remember, the try also check that uh the occurrences on numbers of it was searched before, and based on that, it actually show you the most likely result. So this is what it's saying. This automaton can be transformed into a level 11 Stein automaton which supports efficient search for words within a given edit distance. So this actually support an efficient search for words within a given edit distance. So let's say it was designed to to support until 5 edit distance. So this has its own like structure. It was created for this 5 edit distance. As long as you don't get max this past this 5 edit distance, you would get an efficient fast search for words, because these levels 9 automaton are just designed for that. Other fuzzy search engine techniques go in the direction of document classification and machine learning. See an information retrieval textbook for more detail. So all of the advanced search engine techniques go into the direction of machine learning and document classification, because at the end of the day, you're just classifying where document it is related to, right? What document it is. Keeping everything in memory. The data structures discussed so far in this chapter have all been answers to the limitations of disk. So all of the data structure, the key value, all of the compression are all been discussed due to the limitation of the disk, because disk is not as fast as memory. So we need to create a way. So that's kind of like how it works when your hardware does not cannot give the performance that you can, kind of like in OS, the page swap, right? We create multiple page swap algorithm because of the limitation of disk, because memory is fast now. If our memory is actually big and cost less money, then we won't have this problem. The reason why we're creating this data structure and algorithm is to make the storage of data more efficient. Compared to main memory, disks are awkward to deal with. With both magnetic disk and SSDs, data on disk need to be laid out carefully if you want good performance on reads and writes. However, so you need the data to be organized properly to have fast performance on reads and writes on disk, unlike with RAM. However, we tolerate this awkwardness because disks have two significant advantages. They are durable, their contents are not lost if the power is turned off, and they have a lower cost per gigabyte than RAM. As RAM becomes cheaper, the cost per gigabyte argument is eroded. Many datasets are simply not that big, so it's quite feasible to keep them entirely in memory, potentially distributed across several machines. This has led to the development of in-memory databases. Some in-memory key value stores, such as Memcache, are intended for caching use only, where it's acceptable for data to be lost if a machine is restarted. So Memcache, it's a in-memory, one of the great example of in-memory. It's a key value stores as well, which stores keys and values. and are intended only for caching, which means it's acceptable, kind of like in browser caching, it's acceptable if to be lost when it is restarted. But other in-memory databases aim for durability, which can be achieved with specialized hardware such as battery power RAM, by writing a log of change to a disk, by writing periodic snapshot to the disk, or by replicating the in-memory state to other machines. So these are the four ways to achieve the durability with in-memory. Either you use a battery powered RAM or fixing it through hardware by writing a log of changes to a disk, or separate logs to a disk by writing periodic snapshot to disk. So the most recent, kind of like the version control snapshot, by replicating the in-memory state to other machines, or by replicating that state, that whole state on other machine, or copying the entire data. When an in-memory database is restarted, it needs to reload its state, either from disk or over the network from a replica, unless special hardware is used. So if you choose a replica from other machine, you would use the network type to 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 reload its state. Or if you use the log from disk, you will use your disk. Despite writing to disk, it's still an in-memory database because the disk is merely used as an append-only log for durability. And reads are served entirely from memory. So despite writing to a disk, it's still an in-memory. The disk just serve as an append log for durability. All reads are still served from memory, not disk. The disk does not care about the main data that is being read or written. Writing to disk also has operational advantages. Files on disk can easily be backed up, inspected, and analyzed by external utilities. So the advantage to disk is that it can be analyzed by external utilities. It can be expected and backup as well. Products such as VaultDB, MemSQL, and Oracle times 10 are in-memory database with a relational model. So VaultDB, MemSQL, and Oracle times 10 are in-memory database, in-memory relational database, and the vendor claimed that they can offer big performance improvements by removing all the overheads associated with managing on-disk data structures. So the on-disk, the classic database has a disk, so there's a lot of management needed for database administrator. So these actually claim that they actually remove those. RAM Cloud is an open source in-memory key value store with durability, using a log structured approach for the data in memory as well as the data on disk. So it used the same as LSM3. It's still a memory key value store with durability. Redis and Couchbase provide weak durability by writing to disk asynchronously. Redis and Couchbase still an in-memory key value store, but they provide weak durability by writing to disk asynchronously. So when it crashes, those being written to disk will be lost as well. But RAM Cloud provide the durability by using like some some of the important techniques that makes them in-memory database. Counterintuitively, the performance advantage of an in-memory database is not due to the fact that they don't need to read from disk. Even a disk-based storage engine may never need to read from disk if you have enough memory, because the operating system caches recently used disk blocks in memory anyway. So that's the thing what that people miss is that they forgot that the memory and disk are still running in OS, whether it's Linux, Windows. Um, so those OS will gonna cache that, and those performance doesn't actually come from the need to read from a disk. Rather, they can be faster because they can avoid the overheads of encoding in-memory data structures in a form that can be written to disk. So they avoid that conversion, that state, that transfer from memory to disk. So later we will see how the column storage engine or analytic storage engine also does that. They avoided that completely, the state of transferring from memory to disk, or changing the data structure of memory to occupy the disk. They remove that completely, which makes the scanning of millions of rows fast for data warehouse. Besides performance, another interesting area for in-memory databases is providing data models that are difficult to implement with disk-based indexes. So because of this, you're using memory. There's a data structure that are available there that are difficult to implement in disk. For example, Redis offers a database like interface to various data structures, such as priority queues and sets. So the Redis, their in-memory database offer a kind of like a database like interface where you can um, connect to it like you would connect to a database like a declarative language, and then manipulating it directly, like priority queues and sets that are just not available um, in on disk database, where you need to convert the data from memory to the disk like LSM3s. Because it keeps all data in memory, its implementation is comparatively simple. So counterintuitively, this is actually more simple than you guess than the normal memory to database, because those database a lot of management with the disk, right, to make sure that it is aligned and it is appended and it is organized, and to make sure that it's easy to read and write on the disk. Recent research indicates that an in-memory database architecture could be extended to support datasets larger than the available memory without bringing back the overheads of a disk-centric architecture. The so-called anti-caching approach works by evicting the least recently used data from memory to disk when there's not enough memory, and loading it back to memory when it is accessed again in the future. This is similar to what operating systems do with virtual memory in swap files, but the database can manage memory more efficiently than the OS, as it can work at the granularity of individual records rather than entire memory pages. So because the OS does not have an access to the entire process of the database, remember database is just in the user process, in the application process, it can work on the entirety of records. So Research has shown that you can actually support more than the available memory by using the concept of page swap that we do with OS, where when you don't have enough memory, you swap it. This approach still require indexes to fit entirely in memory. So, though, like Bitca's example at the beginning of the chapter, but still it requires index because again, index makes searching fast from ON to OLAG N. That's how we make the data structure and algorithm of our software fast, and that's how it makes that's how we receive fast response to our computers. Remember as well in the operating system uh, topic, we discussed how the need for interactive has become more and more, especially with about face as well. We discussed how users now require a lot of a fast response to their application because they can always go to other companies. Further changes to storage engine design will probably be needed if non-volatile memory and VM technologies become more widely adopted. At present, this is a new area of research, but it is worth keeping an eye on in the future. So further changes for this data structure will be needed if we adopt this non-volatile memory for SSD, which we already did. So transaction processing or analytics. In the early days of business data processing, a write to the database typically corresponded to a commercial transaction taking place, making a sale, placing an order with a supplier, paying an employee's salary, etc. As databases expanded into areas that didn't involve money changing hands, the term transaction nevertheless stuck, referring to a group of reads and writes that form a logical unit. So a transaction is actually a group of reads and writes that forms a logical unit. A transaction need not necessarily have ACID, atomicity, consistency, isolation, and durability properties, just like with non-relational database. Or even with relational database that has more of these properties. If you configure or if you didn't create the software right, then it will still not create the ACID that most, especially banks, needed. Transaction processing just means allowing clients to make low latency reads and writes as opposed to batch processing jobs, which only run periodically. For example, once per day. We discussed the ACID properties in Chapter 7 and batch processing in Chapter 10. Even though databases started being used for many different kinds of data, comments on blog posts, actions in a game, contacts in an address book, etc., the basic access pattern remains similar to processing business transactions. So even though it's not being used for business transaction anymore, uh, the basic access, that's the key access pattern, is still the same. An application typically looks up a small number of records by some key using an index. So that record is the value, right, in the disk. Records are inserted or updated based on the user's input. Because these applications are interactive, the access pattern became known as online transaction processing. So this is the first type of storage engine we discussed that has the B3 and LSM3. However, databases also started being increasingly used for data analytics, which has very different access patterns. So this data analytics is the second storage engine we will discuss. Usually, an analytic query needs to scan over huge number of records, only reading a few columns per record, and calculates aggregate statistics such as count, sum, or average. rather than returning the raw data to the user. So again, this analytic storage engine needs to scan over a huge number of data, only reading a few columns per record. So it scan a large row and a few columns and calculate aggregate statistics. So it's read heavy rather than write heavy, such as count, sum, or average, rather than returning the raw data to the user. So rather than returning those raw data, it actually execute an operation on that data to make a uh, meaningful data that can be used for the business. So that is just, raw data, but the combination of them that actually would produce business value. For example, if your data is a table of sales transactions, then analytic queries may be: what was the total revenue of each of our stores in January? How many more bananas than usual did we sell during a latest promotion? Which brand of baby food is most often purchased together with brand X diapers? These queries are often written by business analysts and feed into reports that help the management of a company make better decisions, which is business intelligence. So these are the query by business analysts, and they actually communicate to database administrator because scanning or doing this access pattern is actually expensive. In order to differentiate this pattern of using databases from transaction processing, it has been called online analytic processing, or OLAP. So OLTP versus OLAP. The difference between OLTP and OLAP is not always clear, but some typical characteristics are listed in 3.1. The meaning of online in OLAP is unclear. It probably refers to the fact that queries are not just for predefined reports, but the analysts use the OLAP system interactively for explorative queries. So it's unclear actually the OLAP, but it refers to the fact that it actually use an access pattern used to make meaningful connections. So property main read pattern. For OLTP, small number of records per query fetched by key. For analytics, OLAP aggregate over large number of records. Main write pattern. For OLTP, random access, low latency writes from user input. Analytics, OLAP, bulk import, ETL or event stream. Primarily used by for OLTP end user or customer via web application. Analytics, OLAP, internal analyst for decision support. What data represents? OLTP, latest state of data, current point of time. OLAP, analytics, history of events that happen over time. Dataset size, OLTP, gigabytes to terabytes. OLAP, terabytes to petabytes. At first, the same databases were used for both transaction processing and analytics queries. Nevertheless, in the late 1980s and early 1990s, at first, same database were used for both transaction processing and analytic queries. Actually, both of these were used um, the OLAP or the SQL, the main SQL are being used for analytics. But SQL turned out to be quite flexible in this regard. It works well for OLTP type queries as well as OLAP type queries. Nevertheless, in the late 1980s and early 1990s, there was a threat for companies to stop using their OLTP systems for analytic purposes and to run the analytics on a separate database instead. This separate database was called a data warehouse. Data warehousing. An enterprise may have dozens of different transaction processing systems. Systems powering the customer-facing website, controlling point of sale checkout, systems in physical stores, tracking inventory in warehouses, planning routes for vehicles, managing suppliers, administering employees, etc. Each of these systems is complex and needs a team of people to maintain it. So the systems end up operating mostly autonomously from each other. These OLTP systems are usually expected to be highly available and to process transactions with low latency, since they are often crucial to the operation of the business. Database administrators therefore closely guard their OLTP databases. They are usually reluctant to let business analysts run ad hoc analytic queries on an OLTP database. So they actually restrict their business analysts to run an ad hoc or on-demand request OLTP since those queries are often expensive, scanning large parts of the database, which can harm the performance of concurrently executing transactions. A data warehouse, by contrast, is a separate database that analysts can query to their heart's content without affecting OLTP operations. The data warehouse contains a read-only copy of the data in all various OLTP systems in the company. So they restrict, of course, in searching all the OLTP, but there's a separate database, a data warehouse, which is a read-only for all of those data that could be queried by business analysts to their heart's content. Data is extracted from OLTP databases using either periodic data dump or a continuous stream of updates, transformed into an analysis-friendly schema, cleaned up, and then loaded into the data warehouse. So this data is extracted from OLTP databases using a periodic dump or continuous stream of updates. So there's two ways to extract this OLTP to a data warehouse, whether it's through dumping it all or continuous stream of updates, transformed into an analysis-friendly schema, cleaned up, and then loaded into the data warehouse. This process of getting data into the warehouse is known as extract, transform, load, and is illustrated here. So this is actually what ETL means. You get all of the data from OLTP and transfer it to a data warehouse. So the process of taking it there is called extract, transform, load, or ETL. Simplified outline of ETL into a data warehouse. Data warehouse now exists in almost all large enterprises, but in small companies, they're almost unheard of. This is probably because most small companies don't have so many different OLTP systems, and most small companies have small amount of data, small enough that it can be queried in a conventional SQL database or even analyzed in a spreadsheet. In a large company, a lot of heavy lifting is required to do something that is simple in a small company. A big advantage of using a separate data warehouse rather than querying OLTP systems directly for analytics is that warehouse can be optimized for analytic access patterns. So, just want to clarify, the OLTP is the transaction, not yet the analytics part. And another advantage of querying OLTP systems directly for analytics is the data warehouse can be optimized for the said access pattern or analytic access pattern. It turns out that indexing algorithms discussed in the first half of this chapter, so all the indexes optimization we discuss are all just algorithms and data structure that help us optimize the interaction from memory to disk and the OS. But those actually do not work with this type of data warehouse, though they are good or work well for OLTP, but are not very good at answering analytic queries. We will look at storage engines that are optimized for analytics instead. The divergence between OLTP databases and data warehouses. The data model of a data warehouse is most commonly relational because SQL is generally a good fit for analytic queries. So since we mentioned SQL, or actually, though it is used in OLTP, it is actually it is also where the principle are gotten from this data warehouse because SQL is a generally good fit for analytic queries. There are many graphical data analysis tools that generate SQL queries. Another thing is that SQL, though you may think that it can only be used in OLTP, it can also be used in transactional queries. It's also depend on how you would configure the software, this user space software. There are many graphical data analysis tools that generate SQL queries, visualize the result, and allow analysts to explore the data through operations such as drill down and slicing and dicing. So there is actually a lot of graphical interface that you can download on your desktop that will atomically or do this everything for you, generate the SQL queries, visualize the result, and allow your analyst to explore the data. On the surface, a data warehouse and a relational OLTP database look similar because they both have SQL query interface. So another thing is that they both have the similarities of OLTP and OLAP is that they both have SQL query interface. However, the internals of the system can look quite different because they are optimized for different query patterns. Many database vendors now focus on supporting either transaction processing or analytics workload, but not both. So the internals of the system, the configuration would be different though they have the same SQL because they are very optimized for different query patterns. And many database vendors support either of the two, but not both because to differentiate the two because they have different access pattern though they have same interface. Some databases, this SQL interface is also what we mean by saying that the in-memory can now provide a SQL interface that's not available on this SQL interface. Some databases such as Microsoft SQL Server and SAP HANA have support for transaction processing and data warehousing in the same product. So some product support it in the same, some companies support it in the same product. It's just a matter of, clicking one click away. However, they are increasingly becoming two separate storage and query engines, which happens to be accessible through a common SQL interface. Data warehouse vendors such as Teradata, Vertica, SAP HANA, and Axel typically sell their systems under expensive commercial licenses. So this the known data warehouse vendor that provide this software, Teradata, SAP HANA, actually sell this system under expensive commercial licenses. Amazon Redshift is hosted version of Axel. So the Amazon Redshift is where you would host the Access or this data warehouse or the data warehouse deployed version of Axel. More recently, a plethora of open source SQL on Hadoop projects have emerged. They are young but aiming to compete with commercial data warehouse system. So they want to make it free, kind of like how Linux is free. So they make it open source. These include Apic, Hive, Spark QL, Cloudera Impala, Facebook Presto, Apic Tahoe, and Apic Drill. Some of them are based on ideas from Google's Dremel. So a lot of code base or open source are also working to compete because there's some expensive licenses to make this data warehouse software.